Hey folks, happy Wednesday. Sorry I couldn't be in class with you today, but you're going to get to listen to me anyway. I'm going to make a quick little video here, walk you through sort of your activity for today, which should be kind of fun. Hopefully that standard deviation, standard error, normal distribution activity went well for you. Just really quickly, you may want to scribble this down as review because you're going to do these calculations for me in a little bit with your egg experiment. But remember that standard deviation which gets the little sigma symbol. Remember that's a measurement of how spread out data is. And we saw last day examples of this where there were 3 data sets and the average, the mean, all came out at 15, but some of the numbers were really tightly clustered around that mean, and other ones spread all over the place. There was huge variability. So standard deviation is one of the calculations that you're going to do today for your experiment, which I haven't even introduced yet, but we'll get there in a moment. The other thing that we like to calculate is standard error. Which is how far your sample mean so that's from just like the set of the things that you tested, some small set of a big population, how far the sample mean varies from the true population mean. And that's a calculation. Standard error typically is just SE. You're going to do that calculation, or an online calculator is going to do it for you with today's experiment. Now, when you go to work with standard error in today's experiment, and I'll mention this again, it is going to be used to create error bars on a graph. Create error bars on your graph. And what we want to do is we're going to graph 2 times the standard error, 2 times SE. So you're going to get an online calculator to run some numbers for you, and you might get a standard error of, I don't know, let's make up an example. If your standard error was 0.42, if you were to include error bars on a graph that were only 0.42 up and 0.42 down, remember one standard deviation or one standard error from the mean only gives you 68% confidence in your interval, your result. And we want to go further than that. So what we would want to do is we'd want to double that. We would multiply it by 2. We would turn it into 0.84. And then we would graph error bars that go up 0.84 and that go down 0.84. And I'll show you a little example of a graph in a few moments that lists that. But that gives us, if we double the standard error, remember that gives us 95% confidence, which is way better than 68. And you can go 3 standard deviations or 3 standard errors to get 99.7% confidence. But that, to be honest, is just kind of overkill. So working towards your experiment today, I'm going to introduce sort of the style of the experiment. So what you're going to do for me today, or for Miss Spacey, is you are going to run through QCER, is what I call it. Some people just call it CER. This is a way to think about scientific method without thinking about hypotheses and things that maybe you were introduced to like in middle school that were always a little bit confusing. QCER is like scientific method for dummies, which means it works great for Mr. Heinrich. So the Q stands for question. So as scientists, we look at the world around us, we're curious, we ask a question about something that we can see. C is a claim, which is kind of like your hypothesis then. If you go back to the old style scientific method, you're going to make a prediction or a claim about what you think the answer is to your question. You then design an experiment to collect evidence. And based on your evidence, you can substantiate your claim or not, right? Your claim might end up being legitimate, or maybe you found something that's different. But the R stands for the reasoning. So what's the science behind the evidence that you found? And sometimes you have to look that one up, depending on what the experiment is. So question, claim, evidence, reasoning. It's a really nice way to go through an experiment. Let me give you an example of some QCER, an experiment. Actually, a really funny one that I found online. It's just called CER, although they have asked a question. They just took the Q out. So here's an example of a QCER experiment. A fellow did this and won an IG Nobel Prize, like it says here. This is actually a prize awarded by Harvard, so a very prestigious university, for science that's used for educational purposes, but it's like kind of a spoof and kind of funny at the same time. So this fellow did, where is he? Michael Smith, in 2015, did an actual scientific experiment, and it's like in a peer-reviewed journal. I'll bring it up in a moment here, where he won a Nobel Prize for determining the most painful body part to receive a honeybee sting. So his question was, which part of the body does a honeybee sting hurt the most? His claim, you can see here it says a one-sentence answer to the research question. His claim was that the nostril is the most painful location for a honeybee sting. The upper lip is the second most painful. The evidence says provide measurements or observations that support your claim. So Mr. Smith stung himself with honeybees, and on a scale of 1 to 10, he noticed stings at the nostril and upper lip had an average pain rating of 9 and 8.7. So what's kind of crazy is you can go and look up this article, which actually, like I said, is a peer-reviewed science article about this experiment. So even though it's kind of a spoof, I'm saying that in air quotes, this was an actual scientific experiment where he ran statistics. He did the best that he could for just a single guy doing an experiment. So materials and methods. Here it talks about him doing the experiment. The author was the only person stung. So they're admitting that, hey, a sample size of 1 is probably not the greatest. But are you really going to be able to find a whole bunch of people willing to submit themselves to being stung by bees over and over and over again? I know I wouldn't volunteer for that, even in the name of science. So that's probably why we have a sample size of 1. And they're admitting that in this article, right? It's good science. They're saying, hey, there was 1 person. We're not hiding the fact. We just had 1. So what this fellow did, Michael Smith, was he picked 25 sting locations throughout the body. The author self-administered 5 stings per day. It must have been over several days. I don't know. Or maybe it was, I don't know, 5 in total. That part's a little bit dicey. But he's actually done a pretty good job trying to keep some other variables the same. All stings occurred between 9 in the morning and 10 in the morning to avoid time of day effects. Like maybe you're more or less sensitive to pain in the afternoon versus the morning. So we did all the testing at the same time. At least 5 minutes of delay was given between stings. Longer if he could still feel the pain from the previous sting, because you don't want to change the results of the next one. And then the pain was rated by the author as precisely as possible. It's subjective, they're admitting that. But on a scale of 1 to 10, relative to the internal standard, so it talks about somewhere in here, an internal standard, he stung himself on the forearm to get a baseline. And then a numerical rating scale was used to simplify comparisons between bee sting locations. So there's a picture of all the places where he stung himself. Here is, yeah, it's crazy. So to apply the sting, this guy took one for the team, took several for the team. The bee was grabbed by its wings and pressed against the desired sting location. The bee was held against the sting location until the sting was first felt and kept at the location for 5 seconds to ensure that the stinger would penetrate the skin. The bee was pulled away after 5 seconds, leaving the stinger in the skin. They left the stinger in the skin for 60 seconds, 1 minute, and then removed with 4 steps. So he did that multiple times all over his body and then rated it with a pain scale. And here are the places that he stung himself with the average rating. And then you can see he did calculate a standard deviation even to run some statistics to see. So he must have been stinging himself multiple times in these locations over a number of days. You can see then that he had some variation in the pain rating in some spots. But you've got like skull, middle toe tip, upper arm, his buttock, calf, lower back, upper thigh, wrist, foot arch. I can't imagine that one feeling very good. Oh, he rated it the same as a forearm. That's surprising. Back of knee. I would expect that to be pretty sore. So this is like the lowest. This is the highest, but there's more. Scroll down. So what if we get into the higher pain areas? Behind the ear, top of the hand, top of the foot, abdomen, middle fingertip. So like right on the tip of your finger. I can't imagine that would feel very good. Nipple, armpit, cheek. We're getting more painful. Palm. Oh my gosh. Males in the room are cringing. Females in the room are probably laughing at the males that are cringing. I had said this fellow took some for the team. I would definitely say so. So we had some stings in the important parts. And that was actually less painful than the upper lip or the nostril by far, which is interesting. So you can see based on his testing, his claim is that the upper lip and the nostril are the two most painful spots to be stung by a bee. I don't know that I would want to sting myself in any of those spots. But hey, we'll let somebody else do it and look at the results and laugh about them or cringe about them. So going back to this poster that he created in the end. So there's the evidence he collected to make his claim. And then he tried to come up with some reasoning. So scientific principles to explain the evidence. He doesn't actually know. I don't know if anybody knows. But he came up with, I think, some really great ideas. Why are the nostril and upper lip the most painful spots? So he came up with 3 plausible reasons. Number 1, pain is more intense at locations with thinner skin. That could be. I don't have any tattoos, but I've heard from people with tattoos that places like your ribs where the skin is thin, that hurts really bad. I've heard that your skull, your scalp, skin's really thin. I've heard that hurts. Again, I'm not going to subject myself to that, but we'll let other people do it and they can tell me about it. Or number 2, it could be that reaction to pain is greater at, in quotes, important body locations, like openings for protection. So maybe you've got more pain receptors at places like your nostrils and your lips because you really don't want the bees getting in there, right? Places that your body's trying to protect. Or it could be that measured neural activity shows increased sensitivity at thumb, tongue, lips, and digits. So maybe it's just that places that have more nerve endings in general, more neural activity, are going to be more sensitive to pain. So 3 plausible biological reasons. I think all 3 reasons are fantastic ideas. And you would have to then come up with future experiments if you wanted to sort out which is the actual reason from those 3. But I don't think this fellow did. He probably had enough with his one bee sting experiment, I'm sure. So there's an example of some CER science or QCER science. And we are going to do something very similar to that, but much safer today. So today's experiment for you guys is evaluating a claim and gathering some evidence. We are going to look at, I'm going to call it weekday eggs because it's based on a commercial where they talk about weekday eggs cooking faster than weekend eggs. It's an old commercial that I don't even think you can find anymore. But I really like eggs. And again, I might have mentioned the other day, what we're going to do is actually a comparison here between the true size of large eggs from Walmart and extra large eggs from Walmart. So I kind of came up with this idea for testing eggs by looking at some other items that were for sale and looking at claims that people make to try to get you to spend your money on their products. A lot of these are scientific, and I'm saying that in air quotes, scientific claims that if you actually think about them are really hard to figure out what the heck they're talking about. So I want us to be critical thinkers always of science and math. So if you look at these claims like Cascade Platinum removes grease 10 times better than other brands. So they've given us a number with no range, no standard deviation, no standard error, nothing like that, probably just an average. We have no idea if there's a statistically significant difference between the cleaning power of Cascade Platinum and something else. Because if you go to research this, there is no evidence. They have not provided any of those numbers. So 10 times better than other brands. And then I really like this Crest 3D white strips. Clinically proven. So clinically proven actually doesn't mean anything. People, I think, put that word clinically in there because it makes people think of a clinic. And people walking around in lab coats and you're like, oh, science. But clinically proven means nothing at all. And it says here to whiten teeth up to 7 shades whiter in only 5 days. So I don't know about you, but I have no idea about this like magical teeth whiteness shading scale that apparently exists somewhere. Maybe I'm just missing out. Maybe you guys have like sitting in your bathroom, stuck to the mirror, some like teeth whitening scale where you can hold up all the different shades of light against your teeth and go, ooh, I'm at shade 3. But I don't think such a thing exists. So when we're proving that these strips whiten teeth up to 7 shades whiter, what are we comparing that to? Like how do they know it's 7 shades? How do they know they didn't just get a tiny little bit whiter? Like it wasn't 3 shades or 5 shades, it was 7 shades? What does that even mean? So it's crazy, right? If you really think about it, nobody really knows what that means. I don't know if it means anything, but they want you to spend their money on their products. So what I'm going to get you guys to do today is we're going to go through some question, claim, evidence, reasoning. The question for today is going to be a little conspiracy theory thing here. I love eggs. We eat in my family eggs every morning, and I cook them every morning. So I cook between 4 and 6 eggs every day for breakfast for myself and my family, and sometimes more eggs in a day if we decide to have breakfast for dinner, which I think is great. Eggs anytime? Heck yeah. Bacon anytime? Heck yeah. So the question that I want us to answer is one that I've been wondering about. I always buy the extra large eggs because I want the most egg. I love them. But when I open a package of extra large eggs and look at them and put them beside a package of large eggs and I'm looking at them, I visually can't really tell a difference, but there is a price difference. So what I want us to try to figure out today is there a statistically significant difference between the extra large eggs and the large eggs when we account for the variation that we're going to find in the package? Right? There's more than just averages. We have to then calculate standard deviation. We're going to calculate standard error, double the standard error, like I mentioned earlier, and then we can actually figure out if the extra large eggs are indeed bigger than the large eggs. And I hope they are. I hope I haven't been getting ripped off all these years, to be honest. So the question that we want answered today, are extra large eggs larger? are they actually any bigger than large eggs? Because the price tag is bigger. So what we're going to do is actually go in a slightly reverse order here. That's the question. We're going to collect some evidence. That's your job today, to do a little experiment. And then based on that evidence, we can go back and we can make the claim that yes, the extra large eggs are larger than the large eggs, or they're not. And we'll have to make a graph before we can see that. So what you're going to need to do is, it says 2 weekday eggs and weekend eggs. That's out. Oh, low battery. Hold on. Got to plug in my computer. Okay, sorry. Old computer. Caught it just before it died. Batteries go quick. So what I'm going to need you to do is, I think we have 5 electronic balances in the room. So if we have 10 students, if you can pair up and go in pairs, make sure you keep your masks on, please. You can pair up, and I want you to measure at least 12. So this is the minimum. I want you to measure the mass using the electronic balance. We don't need a ruler or string if yours says that, but you need to use the electronic balance to measure the mass of 12 at the minimum. Try to get more if you can. 12 large eggs and at least 12 extra large eggs. And so groups will have to share the eggs, right? So you can grab a couple of one type and measure them and then do some swaps and stuff like that. The eggs are raw, so safety considerations, don't drop them because they're going to splat on the floor. And I actually do need these for the next group tomorrow, so try not to break any, obviously. Thank you very much. But do a minimum of 12 each. Just because our stats are better, the more eggs that we record, or the more eggs that you record. So minimum 12 large, minimum 12 extra large, a dozen of each. And be a little bit careful when you're measuring the masses on the scales. Most of them, I think, are in a little plastic container, or you can put the lid on the top and then tear it or zero it out. So make sure when you're using the electronic balance, you want the units of grams. So it's a little g for grams. You don't want the units to be GN. So that's what you don't want. That's grains. Mr. Waterman sewered me one time and did some measuring for me in grains, and it screwed something up. Love Mr. Waterman. Don't worry. So you want grams, which should show a little lowercase g. And if you've got the lid on there to kind of contain the egg so it doesn't roll off, then when you put the lid on, just hit the tear button, I think it's called. I don't remember what these little electronic balances look like when I'm not looking at one. But you can zero it out, and then you can pop your egg on there carefully and figure out the mass of them. So 12 of each, record all those numbers. So maybe make yourself a little data table. And just one person needs to make the data table, because the group you're each going to make your own graph, but you're going to be working off the same data. So have your data table. Maybe there's like a large, extra large, and then you got your data sets, all the different masses you're measuring. And you're working down that way. And then what I want you to do is, once you've got those data points or your data measured, and you know what, if it goes really quickly and you're looking at the clock and you got lots of time, take more than 12, do 20, do 24, do 2 dozen, right? This is what I've got planned for us for today. And if you're done with 30 minutes to spare, you're just going to be sitting there picking your nose or playing on your phone. So make sure you get lots of good data. Might as well do some science while we're here. So you're going to collect all that information. And then what you're going to do is you're going to head to the website, because I've got a link to a good online calculator that's going to do the stats for you. So if you go to the homepage for the course, which again we went to last day, and you've got that QR code on your course outline if you need to get there. If you click on Biology 11, but don't click any of the individual pages, like just click the Biology 11, hopefully you can get to this page. And you can see that what I've done for you is I've got the document that we're working from there if you need it for some reason. But then there's a button here that says get your stats info here. So if you click on that, it's going to take you to a second page where you plug in your values that you recorded for all the masses of your eggs. So again, I'm going to just try a few here. Hopefully you can see this. 7.5 grams, 8.1 grams, 7.8 grams, 8.0 grams, whatever it is. There's going to be some variation. So you type those things in there. I tried it with a space. Let's see if it works between the numbers. Okay, it got angry with a space in there. So let's try taking the space out. There you go. So type the numbers in, separated by commas. Don't put a space in, like I did the first time. What's cool is the three things that I want you to calculate for your data sets, it's done for you. So hey, there's the mean, the average. So that's going to be the height of your bar graph. When you make a bar graph, I'll show you in a moment what that might look like. Your standard deviation, it's a useful number, but we're actually not going to use it. The standard error is what we want. And let's say maybe go to like 2 decimal places for this, this graph. So we'll call it 7.85 for the mean. The standard deviation is 0.26 and the standard error is 0.13. So when I go to make a graph, my bar on the graph is going to be at a height of 7.85. Then I'm going to take this 0.13 standard error and double it, which is 0.26. And that's going to be the size of my error bars on the graph. And I'm going to do that for the large eggs. And then I'm going to do that for the extra large eggs. And it's going to make us a graph. So let me sketch what that might look like for you. This part you don't have to write in. We've already talked about the calculations for mean, standard deviation, standard error. And we're just going to use the online calculator to do it, so it's all good. Hold on, let me see if I can actually pull that graph paper up that you're working from. The green one, the green graph paper. All right, so you've got a piece of graph paper like this. You're going to graph the results. There are rulers, I think, in front of the teacher desk there. I don't have a ruler. I'm sitting in my basement here, but it would be nice if you could make a good looking graph by using a ruler for all the straight lines. So do as I say, not as I do. I'm not going to use a ruler, but it would be nice if you could. Again, make it look nice. Take some pride in it. Each partner is going to make their own graph. So try that. You're just going to make a bar graph. One bar is going to be the large eggs. And this is just an example, right? It doesn't have to look exactly like mine. You could probably make yours look better. One bar is going to be extra large eggs. Oh, look, see, I have things with capitals and not. Let's make it the same. You'll need to figure out a scale for your bar graph. And if I go back to the numbers that I used, these are just made up, right? I need to get up to like 7.85 and then put some error bars on. So you can play around with how you work your scale. Like, I don't know, maybe I want to go every box. I'm talking about these bigger boxes. Every box maybe at 0.5, which means every second box would be 1. And then if you want, you can actually just label every second box because we can easily see that every box is worth 0.5, 2, 3, 4. But you might scale by 1s depending on how high you need to get to, or 2s or 5s. Try to scale by nice numbers just because it'll make your life a little bit easier when you go to actually plot the numbers. 6, 7, 8. So mine might look something like that. And let's say that I have to plot the bar for the large eggs at 7.85. That is going to be right about, let's see, where did I put that name? It's going to be like somewhere in here. Again, if I had a ruler, I could make this way nicer. So that's going to be my X bar. So again, use a ruler, make it look good. That's going to be what one bar looks like. Kind of nice to title actually the other axis probably as well. So this would be mass of the eggs in grams. And we might as well go all out and give this graph a title as well. So this is, give it a simple title. You can change it if you want. It's all good. Mass of eggs. You could be more descriptive if you'd like. Grab your ruler. I don't have one. I apologize. Make a straight line. So what I'd like you to do is create these bar graphs. I'll just show the large eggs one here. So because it might be hard to see for people exactly what that is, it's always nice to go and label your average. So you could say X bar equals 7.85 G for grams. I think that's what it was. Yeah, 7.85. And then I have to put these error bars of my standard error times 2 because we want that 95% confidence. So now I'm going to go up 0.26 and down 0.26. So if I do that, you can ballpark where it goes, and then I'm going to get you to actually show the numbers. So 0.26 is going to take me to, I don't know, we'll go quickly, maybe about right there. And then down 0.26 might take me to about right there. So there's my 2 times the standard error bars. Now, because it's, again, maybe hard to read where exactly those sort of points are, I'd like you to actually calculate them and write them in there. So show me what is the number on the top end and show me what is the number on the bottom end. So on mine, if I add 2 times the standard error, if I add the 0.26, that takes me to 8.11 grams. And if I subtract 0.26, take that away from my X bar, that's going to take me to 7.59 G for grams. And it's just nice, then we can see exactly where the bar goes up to, and then we can see that sort of range. So we're 95% confident that these eggs are between 8.11 grams on the high end and 7.59 grams on the low end. So you're going to do that as well for the extra large eggs. Again, I hope they turn out bigger. So you'll have another bar coming up on this side. Maybe it's going to look like that. Wow, that looks terrible. Sorry, guys. Throw your doubled standard error bars on there. Show numbers for all this stuff. Make it look just like the first one. And then remember, what's key for us is whether or not we see overlap between these error bars. So if we use this as my example, if these are the large eggs, notice that there's where that bar goes to. The low end of the extra large eggs, that's where the bar goes to. There is no overlap. So if you run into this scenario, you would say that there is a statistically significant difference between the size of the extra large eggs and the large eggs. So in this case, the extra large eggs you have proven to be larger than the large eggs, which is again what I'm hoping for. But if you end up creating a graph that doesn't quite look like that, let's say you plot your X bar and it goes up to here, and you might go, oh yeah, they're bigger, right? The average is bigger. Yeah, well, what if your uncertainty bars do that? So notice now that we run into an issue, right? There is overlap. So that one goes to there and it overlaps on that bar, which overlaps right here. So we've got this region of overlap in here. And because there's overlap, that means there is no statistically significant difference between the egg sizes. So it's more than just the averages. If we see the overlap, it means that, hey, they're actually the same size, even though you're paying more for the extra large eggs. So try creating that graph. We can always chat about this the next time I see you. Make that graph, just hang on to it for now. I will collect the graphs from everybody when I see you again on Friday, I think, if I got my days right. And again, you can ask any questions on Friday if you need. It's not a big deal. We can take a few minutes to go over this if we want. Otherwise, have fun playing with eggs. And like I say, we'll see you on Friday. Any questions, you can always fire me an email or just save them. Thanks for suffering through a video that was much longer than I thought it was going to be. But now you get to go play for the rest of the day. So enjoy yourself. See you in a couple days.